All right, welcome back. We're now getting started with chapter 3, which is motion in 2 dimensions, and it's important that you are up to speed with motion in 1 dimension in order to understand this material. So it gets to be a snowball effect if you haven't learned the previous subject matter, because this next section will depend on what we learned in chapters 1 and 2. So the idea then with 2-dimensional motion is that we have motion in a plane rather than motion just along a line. So before in chapter 2, motion along the line could be this way, say, or that way, or it could have been at some diagonal line too, but usually it would just be horizontal or vertical. But with motion in 2 dimensions, we have motion up and down and back and forth. And so both of those together give rise to a slightly more complicated problem in which we have to use components of vectors. So in general, if we have an r vector, we can break that up into its x and its y components if we have chosen a coordinate system that points, say, in the x and the y direction. And remember that in order to have a vector, we need to have a magnitude and a direction. So here, the magnitude of the vector r, and this could be a velocity vector and acceleration vector too. It doesn't necessarily just need to be a position vector. But in this case it is. And so we have this direction then defined by theta, measured from the x-axis. And so we have an x component to that vector, which is just r cosine theta. And we have a y component to this vector that is just r sine theta. And this, of course, comes from the definition of cosine and sine. Cosine is rx over r. So just cross multiply and you get rx as r cosine theta. Sine theta is ry over r, so therefore ry is r sine theta. And then you can also get the magnitude of r. We can just flip up here to the upper screen, and we see that r magnitude is just the square root of rx squared plus ry squared. And theta, the tangent of theta, is ry over rx. So theta is the inverse tangent of ry over rx. Just a little bit of a review. We already had covered that in chapter 1. Okay, and so one of the things that is, I think, most interesting to look at with 2-dimensional motion is a constant acceleration motion in the vertical direction, which we'll call projectile motion. Now in projectile motion, we normally fire some object off. It might be a cannonball, or in this case, it could be a clown being fired out of a cannon. If that's the case, then I hope he's getting paid enough for this. Let's say in this case, the velocity that the clown is fired is 100 meters per second and fired off at say a 30-degree angle to the horizontal. Okay, so if that's the case, let's say that the clown moves along what we'll see is a parabolic path and then eventually lands at some distance away. And so here we might have a big net to catch him, trampoline, or something, but then he'd bounce. So this may be his last great stunt, but hopefully not. Hopefully the clown will be okay. And so here, what we're going to need to do is break this up into 2 different motions. So that's our strategy in these projectile motion problems. We take vector components then solve the x and the y motions separately. Okay, so how would we do that? Well, in this case, let's say that we want to know what the x displacement or horizontal range is for the clown. It's fired at 100 meters per second, and let's assume the clown lands at the same height from which he is shot. So in solving the x and the y motions, the thing that separates the x motions from the y motions is the fact that in the x direction there's no acceleration. So we can just say that x equals vx times t, where vx is the x component of the velocity. So that means that we're going to need to break up the velocity vector, which is off at this 30-degree angle, into x and y components, where vy is v sine theta from before, and vx is v cosine theta. Okay, and then because there's no acceleration in the x direction, this we could write as v0t plus 1/2 at squared from that third kinematics equation. But the acceleration is 0 in the x direction. So it's a simpler equation even than that. It's just rate times time equals distance. But looking only at the x component. So in other words, as the clown moves along, the y component gets smaller, but the x component remains constant because there's nothing to accelerate the clown in the x direction, except for air resistance, and we're going to neglect that here. So whatever we find for Vx, it's going to stay the same value all the way through. And then Vy is the part that starts out positive, then shrinks to 0, and then it's the Vy then that starts to pick up as a larger and larger negative value on the way back down. Okay, so the y component of the velocity is very much like an object which is just thrown upward with an initial velocity and then moves in a one-dimensional path with constant acceleration. Okay, so this is the x motion, very simple. But the y motion involves our 4 kinematics equations. But now it's at the y component of velocity. So we have Vy final equals Vy initial plus At. So this would be Vy final here, and this would be Vy initial here. Because this would be the initial point, and that would be the final point, and the y component of velocity is changing all the way through. And then our second equation would be y equals 1/2 times Vy initial plus Vy final times t. So it's the same as before, except just with the components of the vectors. So if you just take our kinematics equations from chapter 2 and you plug in a little y there for the y part of the velocity, then we have the same equations that we had before. Okay, and so in this problem, first, let's just find x, which is the horizontal range. and it's fired at an initial velocity of 100 meters per second. So that means that we need to do a couple of calculations. We need Vx. So Vx is equal to 100 times the cosine of 30. Okay, and so that's going to be 100 times, and then have our little reference triangle handy here. 1 to root 3. So the cosine of 30 is root 3 over 2. And so that gives us 86.6 meters per second. Okay. The square root of 3 is 1.73 divided by 2 is 0.866. And 0.866 times 100 is 86.6. So if we look at the x equation, then we have Vx is known, already given in the problem, but the time of flight is not known. We don't know the time of flight. So where can we get that? Well, typically in these problems, we want to get the time of flight from the y equations. So what we need to do then is ask ourselves an equivalent question. That question being, if I throw an object upward with an initial velocity that's equal to, in this case, Vy would be equal to 100 times the sine of 30. Sine of 30 is 1/2, or 50 meters per second. Let's just pretend now that we're throwing an object upward with an initial velocity of 50 meters per second. And we've actually already solved that problem in chapter 2. We did an example where the initial vertical velocity is 50 meters per second. Because what we're doing is we're saying this motion, throwing it up and then having it come back, is superimposed on this motion, which is just rate times time equals distance. And so this is a very important concept for you to get now so that you don't make mistakes with this later. Some of the main problems that people have in solving these problems is not putting in the components. And when you see a Vy final or something, putting in a 100. And so that would be considered a catastrophic error in a problem like this, and you'd get marked up severely. So be sure that that doesn't happen. All right, so what we need then is the time of flight, and we can get that from the y equations. And then we'll take that value for the time of flight and plug it back in to the x equations. Now if we throw an object up, it'll reach the peak of the path in half the total time of flight. So that's the way I'm going to approach this problem, is I'm going to find the time to the peak, and then I'm going to double it. Okay, so if we do that, then we can set up a table of knowns and unknowns, just like we did in chapter 2. I hope you're getting good at this by now. So Vy initial would be plus 50 meters per second. Here we've defined our positive direction to be up and to the right. The acceleration due to gravity in the vertical direction is down. And so the acceleration is minus 10 meters per second squared. And the Vy final is 0. Okay. Now I could have just as easily gone to this point and said that Vy final is minus Vy initial. That would also be fine. But here, I'm just going to go to the peak of the path and then double it. All right, so our unknowns then are the time of flight, t, and the y displacement. And so I'm going to get rid of all of the equations over here that involve the y displacement. And this gives me an expression for the time in terms of Vy final, which is 0, and Vy initial, which is plus 50, and acceleration, which is minus 10. So t then is going to be Vy final minus Vy initial over the acceleration, or 0 minus 50 meters per second divided by minus 10 meters per second squared. So that gives me minus 50 divided by minus 10 is plus 5 seconds. Now you may recall that we've actually already done this problem before. We figured out the time to the peak, and also the y displacement at the peak was 125 meters in a previous example we did. So this should be reasonable to you. And again, the reason why that would be reasonable is it would go from 50 to 40 to 30 to 20 to 10 to 0. So that would take 5 seconds to slow down from 50 to 40 to 30 to 20 to 10 to 0. 5 seconds. So that's a reasonable answer. Then once we have that value for the time, we can plug back into our x equation. And so our x equation then is going to be x is equal to 100 times the cosine of 30, so that's 86.6 times, now is it 5 that we're looking for here if it's the total time of flight, or does that just give us half of the horizontal range? Think about that for a second. Turns out that this time is only half the time, as I mentioned before, that we need. And so 2 times t to the peak is equal to t total. So that would be 10 seconds. So it's 10 seconds that goes in here, not 5. So that gives us then 866 meters. So that's something like half a mile, pretty significant distance. So that's our horizontal range. Okay, so what did we do again? Well, we looked at the x part of the motion. We saw that we had the x component of velocity and that remained constant throughout the motion. But the time of flight was not available unless we go to the y equation. So we picked the y equation that gave us the time of flight in one step, and then we plugged that value back into the x equation and solved for the horizontal range. Okay, so that's the first problem I wanted to do to illustrate this whole idea of projectile motion. But there are other things we can do as well. Let's keep the initial conditions the same. In other words, we've got the clone being fired out of the cannon so that the x and the y components of velocity are the same. But now let's say that instead of this being a clown being fired out of a cannon, that it is a baseball. And for our example here, let's say that the baseball is hit all the way out of the park. Okay, so far out of the park, going, gone. And somebody's listening to the baseball game with their radio that lives nearby and is in the 10th, let me see, say it's 10 meters high above the ground. Okay, so maybe that would be like 30 feet, so maybe the 3rd floor of a building, something like that. And let's ask, what is the velocity of the ball when it's caught at 10 meters above the height from which it is fired? or if it's a baseball, to be hit. Okay, so this y displacement then is 10 meters. And so we can't any longer say that we know what the time of flight is to that point. We do know it's going to be somewhere between 5 seconds and 10 seconds, and maybe a little closer to 10 seconds. But we can't say for sure what that's going to be without doing some calculations. And we're not asked for the x equations, although we should know that the x component of velocity stays constant all the way through. So that means that this x part of the velocity is going to be part of our calculation later on. And so here we can get ready for finding the final velocity by knowing that this is Vx, and that'll be 86.6 meters per second. The Vy final is not known yet. And we can't get V final, which is the resultant vector, or the angle theta, theta final, until we've done some calculations. And so we're going to need to find Vy final, which means, again, that we have to go back to our y equations of motion. But for a problem where the final displacement that is associated with this motion is plus 10 meters. So, and let's keep in mind here that in this problem, the total displacement is the displacement to the top, which we showed in a previous problem was 125 meters, plus the displacement back down to this point. But that's just from the tail of the first to the head of the second, is just our y displacement. So our y displacement is 10 meters. So if we set up a table of knowns and unknowns, just like we did before, then we have Vy initial is 50 meters per second. Acceleration is equal to minus 10 meters per second squared, and y is equal to 10 meters. Our unknown quantities here are going to be Vy final and the time of flight. Now, nowhere in the problem have we been asked to find the time of flight. Okay, that's the time to that point. I could calculate that later if I wanted to, but what we'd want to do is get rid of all the equations involving the unknown that's not asked for. Remember, that's step 3 of our one-dimensional kinematics equations solution steps. And so that leaves us with this last equation then to find V final. Okay, so Vy final then squared is equal to Vy initial squared plus 2ay. All right, so Vy final squared is going to equal 50 meters per second squared plus 2 times minus 10 meters per second squared times 10 meters. Okay, this is squared. And so that'll give us Vy final is plus or minus the square root of 2,500 minus, this is going to be 200. So that would be the square root of 2,300 plus or minus. And so that would be plus or minus 47.3 meters per second. Okay, now, which solution do we want, the positive or the negative? Well, clearly here, the final y velocity at the point that it's caught is going to be the negative one. Is there a positive solution? Yes. The Vy final on the way up would be positive at plus 10 on its way up. So actually both solutions here do represent physical parts of the problem, but the one that is relevant for our calculation here is going to be the negative root. And so a lot of times you get to this point and you figure, oh, I did it, I'm done. And then you move on. And that's true, you're done if you stop here, but you're done with a maybe 3 out of 10 deduction because you haven't recomposed your vector yet. Okay, so what we're going to want to do here is write this as Vy final is minus 47 meters per second. And then V final we can get as the square root of 47 squared plus 86.6 squared, just like we did before in that previous example. So that gives us approximately 49 meters per second. I'm sorry, 99. Is that a reasonable answer? Well, this is 100 that we start out with as our total velocity vector. And then on the way back down, we haven't quite picked up the full Vy, because remember, if we got back down to the height that was released, we would not be at minus 47 anymore, we'd be at minus 50. Okay, so minus 47 is a reasonable answer here, and 99 is a little less than 100 because it's almost back down, but not quite. And then you could write the angle, theta, as being equal to the inverse tan of Vy final over Vx. Now, the tangent function is, in fact, all students take calculus. So it's positive in the third quadrant, it's negative in the fourth quadrant. So if you plug this in as a negative value, you'll get a negative value for the angle. Or you can just keep this positive and realize that you're measuring the angle from the horizontal, and that's also acceptable. So that's the way I'm going to do it here. Theta final is just equal to the inverse tan minus 1 of 47.3 divided by 86.6. The units cancel out. That gives us 28.9 degrees, the theta final. Now this, I think you can make an argument, is also a reasonable answer because Vy has not quite expanded out to the full value that it would have, and here it would have to be 30 for the angle. So if Vy isn't quite negative 50 yet, then this angle here, 29 or 28.9 degrees, is about right. So that's a reasonable result. And so that's something that in so many of these problems we can do. We can look and see whether our answer is reasonable, and that way we can catch errors. Whereas if we're just hoping that we did the right thing, then we don't have that ability to catch the errors. Now, how would this problem change if I had the mass drop down below the height from which it is released? Think about that. Let's say I had it be caught down here at a point that's 10 meters, like in a subway or something. The ball goes up and it goes through the stairwell of the subway, and then somebody with a catcher's mitt down here snags it. It's going to be going faster than 100 if it's down here. And y would be minus 10 at this point. Okay, so the x component would be the same, for 86.6, but the y component would be more than minus 50. in the negative direction. The angle would be more than 30. And when you plug in, the only thing that would really change is that you'd have a negative sign here. The y displacement would be negative 10. If it were negative 10, then you'd have a negative 10 here. That would make this a positive. So that would be the square root of 2,700, which would be something like 53 meters per second. Okay. Rather than minus 47, it would be minus 53 if this were a plus 200 here. And here I'm assuming that it dropped down 10 meters below the height rather than being 10 meters above the height. All right, so that would still be a reasonable answer, and you could solve that kind of a problem too with the same exact procedure, just by realizing that the net displacement would be this vector plus this vector. So that would be a minus 10. That would be your y displacement would be minus 10. And then that minus 10 would go in there. And you just basically do the same thing that you did before.